So in our last video, we were still looking at a point charge, and that the electric field is spreading out from it in every direction, and we used Gauss's law to reproduce what we knew was the field for this point charge by considering how much flux went through a bubble, and the symmetry of the bubble is the same as the symmetry of this point charge. A point charge has 0 dimensions. It has 0 length, 0 width, 0 height. So, great. We've got Gauss's law, and just like I said, Gauss's law is always true, but not always useful. So in this video, we want to do something more complicated than looking at a point charge. I want to figure out the field due to something more complicated. More complicated, but still totally unrealistic, because this is introductory physics, so, well, a little bit more advanced. But I went to, you have to order things online now only, so I went to infinitelinesofcharge.com and I ordered myself an infinite line of charge. How long is it? It's so long I can't see the ends. It's very long. What would the field look like due to this line of charge? Let's suppose it has a positive charge Q on it. And I want to know, how strong is the field some distance away from it, some distance r? Well, what do we know is going to happen as I get further from the line of charge? I know the field will be pointing away from this line of charge because it's positive. And I know it's going to get weaker. It makes sense to me it would get weaker as I get further away. But how would I actually figure that out? Well, Coulomb's law, do you remember Coulomb's law? It says that the force due to some charge is equal to this constant KEQ times the other Q over r squared. But now we're not talking about electric force, we're just talking about electric field, which is the force per charge, so we're going to get rid of one of these Q's. So the electric field is just KEQ over r squared, but this only works only for point charges. So if I have anything more complicated, and the least more complicated I could get maybe is a single line like this of infinite length charge, how am I going to figure this out? Well, I know due to this little bit of charge here, I'm going to have an electric field like this. And due to this little bit of charge here, I'm going to have a bit of electric field like it's going to be longer because it's closer. And due to this bit of charge here, in this direction, it's going to be even longer because it's closer. And due to this bit of charge, I'm going to have more field. It's going to be like this. So I need to vector sum all these guys from infinity to infinity, positive to negative infinity. And that sounds complicated. I'd have to do some kind of integral with cosines in it. That does not sound like the way I want to do this. I will do that in another video. But to show you the easiest way to do this, we're going to use Gauss's law. Always true, not always useful, but let's make it useful. So I've got my infinite line of charge, and what will my electric field look like? Well, for every bit of charge up here, every little bit dq, I've got another little bit dq here in the other direction. So what would those vectors look like? This one would point this way, this one would point this way, and the result would be all the vertical parts would cancel out, and I'd only have field pointing away from this this stick, this infinite line of charge. What if I looked down on top of the stick of charge? Here we got a bird's eye view. I know the field would point away in every direction. So this looks like the kind of brush you use to clean out a test tube or a bottle brush, or maybe a round brush if you want to curl your hair. So the electric field would point everywhere away from the brush, like this. So I want something that has the same kind of symmetry as this field, and I'm ignoring the end. Let's suppose those end effects don't matter. So what kind of object has the same symmetry as a bottle brush? Maybe a delicious can of Amy's organic soup. Quinoa, kale, and red lentil sounds great. So does this have the same symmetry, cylindrical symmetry, as that bottle brush? It looks like it does. So I think I can take advantage of this, make a Gaussian surface shaped like my Amy's organic soup can, and that will help me figure out the flux through this surface, and therefore the field due to this infinite line of charge from where? infinitelinesofcharge.com. So let's do this calculation. I want to make a Gaussian surface. I'm imagining a surface, and what's that surface look like? Let's get another color here. So my surface looks like the soup can. It wraps around this line of charge, and flux goes through it. But what parts of the soup can does the flux go through? Let's see. Well, we know it only points normal to the soup can surface. Points all around here, like the bristles of that bottle brush. Does any flux point through the lid? Well, the field only points away from this. It doesn't point up or down, so there's not going to be any flux through the lid, and that's why this works. I've got this soup can that has this symmetry I can take advantage of. So let's remember, what is Gauss's law? It says that the electric flux through a closed surface is going to be, let's see, by definition, the electric flux through that closed surface, remember we have a closed integral here, over the surface of the electric field dotted with the area vector all around. Am I going to care about that dot? No, I won't, because E is everywhere perpendicular to the label of this soup can, and it doesn't even go through the top or bottom of the soup can. It only goes through the label. So, Gauss's law says that this is just the definition of flux. It says that it's equal to the charge enclosed divided by that constant epsilon 0. So why do I care about this? How is this going to be useful? Well, let's see. If I go some distance r away from that stick, distance r, because of the symmetry, this is going to be the same electric field here and over here and everywhere around that circumference, as long as my soup can is the same radius away from the stick everywhere. So what can I do with a constant when I'm thinking about an integral? Whoop, it pulls right through. So the strength of this electric field is going to equal the integral over the area of this soup can where flux goes is going to equal the charge enclosed divided by epsilon 0. So I really need to know how much charge is enclosed and what is this area. So what do we want to do first? Let's figure out how much charge is enclosed. Well, suppose this is an infinitely long charge distribution, but I know it has a charge density. My charge density, lambda, is going to be the charge per unit length, q over some length. And what is that length? It's the length of my Gaussian soup can. So how much charge is enclosed? Well, I have charge per length is lambda. So that means that the charge enclosed, the charge here that's actually inside the can, is going to be the charge per length times the length of the can. So I can just put that in here. So I know that E times this integral over the part of the can that has flux through it, think about what that is before we get there, is going to be the charge per length times the length of the can divided by epsilon 0. So what is that going to be? You might hear a cat walking next to the camera. Great job, cat. All right, so we have the field, the flux through the label of the can. The only thing I care about here is the label, so let's actually unroll this. How big is this rectangle? That's where my flux goes. Not the top, not the bottom, but just the label. So I know the label, this came from a circle, so how long is this thing? It's going to be 2 pi r long, where r is the distance from the stick, and stick of charge. And how tall is this thing? It's this made-up length L that I imagined myself, so why am I allowed to make up a length? We're going to see that. So how big is this area? I know that the area, E times this closed area, this is just the area of the label. So how big is that area? Well, it's 2 pi times the radius. That's how wide this soup label is. And the height is L. So it's just a rectangle who's this big. And that's going to equal the charge per length times the length over epsilon 0. And I see this length which I made up. I don't know if I'm allowed to just make up lengths to solve things, but fortunately I am allowed to because it just cancels out. So how strong is this electric field? Well, we can divide both sides by this 2 pi r, and I see the electric field is just the charge per unit length divided by 2 pi r times that constant epsilon 0. So that's due to a line of charge when I'm a distance r away. Let's compare that to the electric field due to a point charge. We remember that that is the strength of that charge divided by 4 pi epsilon 0 r squared. So I see when I have a 0-dimensional point charge, it's proportional to 1 over r squared, r to the 2. When I have a 1-dimensional distribution of charge that only has a length, my electric field is proportional to r to the -1. So we got r to the -2, r to the -1. What do you think will happen if I have a two-dimensional distribution of charge, like a infinite plane? Well, we will talk about that in the next video.